Okay, so make a start. Since it's such a small group, do feel free to stop me if you want to ask a question. That's no problem at all. It's going to be in two halves. One, I'm going to explain a bit just for fun, just for people that don't know what synchrotrons are, and just have a look at some of the hardware involved because it's rather fun. And in the second half, I'm going to show you some demos of the data analysis software, and explain some of the software development that we do. The product that we're going to look at today is open source. It's on GitHub and we have a website, dawnsci.org. Very much welcome people to contribute or get involved. We would like to donate part of what we've done to Eclipse at some point, so hopefully that'll happen one day. Who am I? So I'm not a proper scientist, but I'm going to lecture you all about science. I'm a software developer, worked in Java for a while, mostly in engineering applications, all over the spectrum really. But for the last 4 years, I've been working with this synchrotron data. I'm a fan of Eclipse. I'm going to try and explain some, hopefully not for enjoyment, not for your Schadenfreude. And then we'll look at the software. Synchrotron, what is it? Cool word, but what does it mean? Well, I think we can clear it all up by saying it's a cyclotron in which the magnetic field strength increases with the energy of particles to keep their orbital radius constant. So that's that. No, what it is it's a machine which basically produces very bright light, and that's used in a whole range of experiments from basically things like spectroscopy, from tomography, macromolecular crystallography, lots of ography words, but basically they're all kind of scientific experiments, although there are a few things which are not scientific experiments. What does it look like? So I worked at the ESRF for a bit, and I've been working at Diamond the last 2 and a bit years. They're big donut buildings. You'll see that the one in France, the ESRF is in France, in Grenoble, is much bigger than Diamond, but actually we're involved. The UK government contributes to the ESRF a little bit, behind Germany and France is the third contributor. And we've used a lot of the technology that we had in that collaboration to build Diamond. And Diamond is actually, although it's smaller, and it's a very brilliant light source, so we can do quite a range of experiments there. You'll notice as well it says user facility for Diamond and experimental facility for the ESRF. So the ESRF are basically figuring out how the technology works, and Diamond are applying it. So it's opened by Her Majesty the Queen on the 19th of October 2007. Inside the machine, inside the donut that we saw earlier, we have basically a Star Trek conduit kind of arrangement with lots of magnets, wires, cooling, supercooling things. It's fantastic. It's a geek's wet dream. Scientists, some of them are shown here. They don't all look like that, you know. Some have got beards, but here they're pictured next to some of their, looking very happy next to some of their experiment. Now, the machine works by a stream of electrons, basically, which I'm going to show you a video in a minute of how it works, but the stream of electrons basically is bent by magnets, and it gives off very bright light. That goes into an experimental hutch, which is like a lead-lined lorry body, basically, if you imagine a great big rectangular cuboidal volume, which is the optics hutch, and in there the light gets treated until it's the correct energy for the experiment. And then these guys are actually sat down in the experimental hutch, where their actual detectors are. So as the light comes in, it hits a sample and something happens, some signal is given off, numbers are recorded somewhere along the line. And they actually can't stand in that enclosure when the experiment's running because it's full of hard X-rays in general. So video time. So this is the outside of the building, and both buildings that I showed have got a kind of a big office block, but that's where all the program is set. So that's obviously the most important area. And the scientists sit around the ring. So you can see those optics hutches and experimental hutches that I mentioned. So where do the electrons come from? They get shot out of a LINAC, which is a linear accelerator there, and it's similar to the back of an old-fashioned telly, so it's basically working with an electron gun. They go into a booster ring, they come out of the booster ring and into the storage ring. Now, in that graphic there, it looks circular. It's actually not circular, it's actually straight sections with magnets bending the electrons at each section. And when the electrons are bent, they give off light. Right, that's going to repeat, so we'll stop that. Okay, so the detectors, basically, everything, all the software we generate, we create is basically just dealing with great big arrays of numbers. And the arrays might be one-dimensional, they might be two-dimensional, three-dimensional, or n-dimensional. But basically, it's just a way of having a great big stream of numbers that are recorded in some way, and then from that file are visualized. So this, in the bottom right, is a Pilatus detector, which is a CCD, which I believe is similar to a digital camera, but it's just a lot bigger. It's just a great big silicon chip. This, in the bottom left here, I haven't got a pointer, but you see this big cooling nitrogen tank, and attached to it is a bunch of germanium elements, and that's used in a spectroscopy experiment. It's got a 64-element array, and so is the one at the top. Okay, so I'm going to move on a bit to software now. Any questions about any of that?
Where in France is the French facility?
Grenoble. Yeah, it's actually in the city there. So Diamond, where I work now, is not actually in a town. It's kind of a bit more out in a science park, but yeah. Do you know Grenoble?
No, I live in Nice, but
okay, yeah.
It's a nice skiing area.
Yeah. Yeah, that's why I moved there. So what the developers do, well, the developers do basically three things, and all of those things involve Eclipse RCP. We're only going to look at one of them today, but we control the experiment. So you remember I said that the scientists cannot be in the hutch because of the hard X-rays. Well, but they still have to move their samples around, and they still have to be able to open and close the shutter to let the light in and all this kind of stuff. So there's basically robots, motors that are moving various geared implements, and we have an Eclipse GUI for moving those around, and also we have Eclipse GUI for setting up the detectors and recording the experiment, designing the experiment, running it, and saving the data. The GUI doesn't save the data, we've got a server for that, but it interacts with the server. And finally, it's the middle one actually that I'm talking about now, is we've got software for data, which is an Eclipse workbench we're going to have a look at. Basically it's going to plot arrays of numbers and allow people to do mathematics of some description, and the description is quite varied, so we have to be very flexible in what we do. And well, the final thing is it's the same maths but done in batch. So we have this capability, kind of a cluster supercomputing capability, such that we can run, typically in the macro crystallography area, we will run known mathematical treatments on the collected data, and that will give things like, which are in that scenario would be called an electron density map, but it depends on the analysis that you want to do. So how do we do it? How do the software developers do it? Well, we use the Eclipse IDE, Newsflash. We use Buckminster, which is really good. So we have like builds. We integrate Buckminster into Jenkins. I've seen actually quite a few people with Jenkins screens around the conference looking at their builds. So it's obviously very popular. From Jenkins, we also run the GUI testing, which we use Squish for. No reason why we use Squish other than we had somebody that knew how to use it. There's Jubiler and other ones which are perfectly good as well. We're not very agile in what we do because we tend to have experts working in certain areas that have got a long history in it, and they're not totally programmers, they're also scientists as well, so they have sort of their own way of working. But we are trying to encourage design documents. We think that's a really good way forward of just writing everything down, writing your design down and getting it right. We use cheat sheets. And we use Git. It's fantastic. We're on GitHub. We really like eGit. Every time I try and describe eGit, I have to add one extra thing that it can do, and it's very much like the Monty Python sketch, if you remember it, where every time it quantifies how good the Spanish Inquisition is, it has to add something else on. And it's exactly the same with Git. It's a fantastic tool. We are building stuff on the shoulders of giants, so we don't, as I think Einstein said, when we program in the Eclipse IDE, like you guys, I'm sure as well, all the APIs that you've got available is just so rich, and nowadays your actual layer that you program is so small and compared to everything that you're utilizing, and that is a fantastic way of working. It's very productive. One developer can do a hell of a lot of code if they do it the right way. A hell of a lot of features if they do it the right way. Some of the things we use sort of draw 2D XY graph. So I believe the XY graph project has just become an Eclipse Nebula, part of Eclipse Nebula. So it's Eclipse Nebula visualization. But we've been using that for some time, and we think it's great. Obviously, we use all the other stuff. We use HDF5, which is a way of recording massive arrays onto disk and interacting with those massive arrays without having them in memory, because typically the information from experiment is too big to fit in memory. So what you're doing is you're always giving someone a view. They're always you're trying to pare down the data and give them a window into part of the data. I'll show you that in a minute. That's some of our architecture as well, just put out in the colourful block diagram form. That's on our website if you want to see that in more detail. You see that we use Python and Jython, mostly CPython. For analysis, the scientists are going to be using things like, I don't know if people have heard of NumPy and SciPy, things like that. That's very popular for the scientific layer. So as well as all this architecture and big stuff, I want to just zoom in into a very small thing, which we find really useful. And I don't know if people have used this SWT Virtual Flag on their trees and tables, but this is brilliant. So if we have, for instance, a table of 10,000 images, we'll use a virtual tree or a virtual table, and it will only actually load the information for the label provider that is seen on screen. So it's very scalable. It only sort of loads stuff as you scroll down. I'll show you that in one of the demos. We use something called a gallery from Nebula, which also has a virtual switch on it. So that way we can have, let's say, 10,000 images or 10,000 whatever, but they're not taking up memory and resources. We have lots of visual tools which I'm hoping to demo. Things like profile boxes, profile mathematics. So I'll demo them in a minute. We've got color mapping and histogramming for if you've got a two-dimensional array. There's different ways you can color the intensity of that in order to bring out certain features of the image. We do other mathematics like peak fitting and line fitting, have function fitting. We have very tailored scientific tools which won't be useful outside of our sphere. The other tools are quite useful. One thing to say about everything, I probably should have said in the architecture, what we've done is we've done everything with extension points. So we're quite Eclipse 3 oriented at the moment. So all the tools are contributed by extension points that I'm going to show you. So they have a plug-in and then an extension point. And then they utilize services. So we have about 30 services, which are things like image histogramming or loading of files. And the services we conjure out of OSGI, and then that gives us our architecture. So we have a completely modular architecture and plug stuff in and out. Do feel free to ask questions. Okay, so demo time, or as you say in Germany, Demo time. Okay, so the first one is going to be showing some of the tools. So this is a single file which contains two-dimensional data, and in that attached to that data we've got lots of different tools which we can use to do with diffraction. We can color the image differently if we choose, so we can see certain features within the image. I think there's a reset here. Doesn't matter. All right. And I can use basically various profile tools. So if I draw a line using this profile tool, it's going to take out the intensities along that line. And you see as it goes through the middle of the image, you've got bigger numbers. And if I move this around, it'll sort of redo the maths based on where that line falls. And we use, you can imagine how you do this. So you have like an Eclipse job, which you basically update and do your maths in, and then it reports back to the GUI. We also have something like a box profile, which is basically doing integration along X and Y. And then you see this. Now you'll see, if you notice, this detector is based on slabs. So they're like silicon slabs in the detector. And then between them, the output is actually nothing useful. So what you can do, there's a masking tool which you can switch on and pick out, remove intensity based on threshold, or you can actually kind of draw stuff on here, basically just random things that you can take out of the picture. Actually reset that, because what I want to do is pull out this grid. So if I take out the grid and I go back to box profile, then I get the numbers without the -2s changing the intensity. I can also do stuff like various sector integration tools. So this is a radial profile. So what this is doing, for those that don't know, is it's basically, if you imagine a line going along each value as if they were the radii of that sector going out, sweeping over the area. It'll do the integration along them and then sum the result. So that means that we'll see these bands as peaks in this plot. And then what we can do is use a tool on that, for instance, one of the fitting tools, fit the peaks. And then those peaks, if I reset this perspective, we're going to see that the fitting tool pops up, I hope. There we go. And then we can actually export the values and all this kind of stuff. And when you slipped on a peak, you see it highlighted.
Do you have several methods for peak finding? So, for example,
yeah.
First derivative, second derivative, or how is it done at the moment?
Well, there's different algorithms that you map to. So pseudo-Foyts, for instance, is very useful. And then you've got various smoothing options, because you can get quite chunky data. So you want to try and fit stuff based on. Sorry.
So like it applies a bit only before a smoothing filter on the data, and then maybe.
Exactly. Yeah. So yeah. Yeah.
Okay, great.
So also, all the graphics are done. There's no reliance on a third-party library for charting, for example. It's done.
No, it's a project. We've got a fork of what the Eclipse Nebula visualization XY graph is now, but we have it before it was. So what we need to do is we need to migrate to the Nebula one, and we're doing that gradually. We're using Philip's IWG group to sort of contact the various people involved, and that seems to be working.
My group, but
Yeah, well, our group.
The transformations are still done. They're all like custom algorithms, or is there Java advanced imaging or anything like that?
I don't know. I did some of the Draw 2D stuff, and that is just basically you have a graphics context, and it's traditional pixel draw that, draw the other. In terms of this image, obviously is bigger than what the image we see there is bigger than the pixels used on screen. So we've got like things like downsampling, and we have various options for the downsampling. So if I go in here, you can change to if you imagine. We're gonna run out of time, by the way, because we're in the first demo and I've got about 5. But so you've got different ideas of downsampling. So you can take a bucket which is say 8 by 8 or 4 by 4, and that's got to fit on one screen pixel. So then you say to that in that bucket, how shall I decide what the value of the pixel I showed to the user is, and that kind of stuff. We haven't used APIs for that. We've just coded it, in fact. Right. So if I go back to the demo, so slicing is another massive thing, and I think hopefully we've got time for some slicing. It's that when they write the data, we just looked at one image, but in fact these detectors can work at tens, or even in the next generation detectors, hundreds of hertz. So these write a lot of images. And so what we're trying to do now is, rather than having directories crammed full of images, we're moving to this HDF5 format I mentioned, and we're trying to make multi-dimensional arrays into single files. So I'll show you some cool stuff. So this is a multi-dimensional array. It's not a massive one. The file's 1 gigabyte, so it's not huge. It has 721K images in them. We can have a look at those. They're in a stack, so it's actually a tomography experiment. So this is a fossil inside a rock, I believe. It's not actually taken at diamond, this data. And we can do stuff like we can pull those out into a gallery. This is where we use the lazy viewer stuff, and we can visualize those. And in fact, if it's, we can also do like 1D slices, and those can be visualized. Sorry, I need to click the right button. Those can be visualized in the gallery as well. There's also the concept of surfaces, which uses Joggle, Java OpenGL, but we're trying to move to Java FX in the coming future. So here we can sort of go over the image and look at it in 3D. And one really cool feature, which I'll show you, is the ability to write expressions which are only evaluated in a lazy way. It's easiest just to show you how it works. So I can do a rolling mean of a expression such as dark. And that's going to take a while because it was a little bit bigger. So yeah, and then I can do the same for the... So what the scientist does is they take a picture of with no beam in there. So they get a dark value for the detector, so they get kind of what the detector would put if there's no input. And then they take a picture with no sample. So then that gives them what it would look like. And I'm taking the mean of those, all of those, that stack of images, I'm taking the mean. It takes a while. And then you can use that to clean up the data. So this is what it looks like without the sample. So all this is noise. So what we can do is add an expression data, which was that original data set. The names are in this column at the end, so I didn't have time to show that. But I can take off the... I need to name these two, actually. It's going to tell me I had a bad expression. I need to go dark mean, white mean, data minus dark. Divided by white. And now we see a much cleaner image. And we can scroll through that. You see it's a much nicer feather. And the other thing we can do then is run all our tools on these stacks. So if we, for instance, if we were doing a zoom of this and we were looking at a particular area within the image, we can run a data reduction tool. I'll do it on the raw data. And actually, I'm going to take out everything. Just finish. And then what that's doing is running the same tool but over the stack. And you can do that for profiles, sectors, and lines, and so forth. And I won't, since we're running out of time, I won't let that go to the end. But we can have a look at that file. So it's only written 75 of the 720. And then we can see the, yeah, that's coming through all right. Right, another cool thing about slicing is so far I've only shown you slicing in axis directions, but actually you should be able to slice in an arbitrary plane, and we're adding more slicing for that kind of ability, but we've got one already at the moment which is pretty cool. So what I'll do is I'll show you this. It's called Hyper 3D. So instead of, as I say, slicing in an axis, we actually can define the plane that we want to slice down. And a cooler color for this is ATFM. And what this image is this isn't our data as well. We're just acting on. This is actually an open source data set. So, and it's not my brain. It's too big. So what this is doing is when I draw this line here, I'm taking a slice down the data set as you look at it along that line. So that surface is shown on the right-hand side. And then when I drag this region on the right-hand side, it's summing all of the images within that area and showing them on the left-hand side. So I can put a plane through, this case, this is the chap's optic nerve in his eye, in his or her eye. And here we can see the back of the optic nerve, but we can also see the signal through that slice of the optic nerve. So it's pretty cool. I know we can move that around and look at different areas. We can look through back through the two halves of the brain. Okay. So we just got up to the brain. Python. So as a Java programmer, my idea of a Python is one of the two above things, but I'm reliably told by scientists that there's another form of Python, which is a programming language which has something called NumPy and SciPy and these are very good for manipulating array data. So if we haven't got GUIs, I mean, I showed you some GUIs, but a lot of the science we don't have GUIs for, and we never will because they're doing very specific tailored things. Then people can dump into the Python layer. So it's another demo. And what I'm going to do, so we have a Python command line. You can interact with any plot, so you can pull out regions. But that on the back of that, we have a connection to Python, which sends our data into something called NumPy arrays. Which so if we can read data and visualize it at any point, we can then send it off to Python, and then they can write some programming with it. So rather than show the console, which as this is beta software, it wasn't working, I'm going to show filtering. So what I'm going to do is apply a very, very simple filter to one of these images. Doesn't really matter what this one will do. Call that. Well, actually, I don't have to name the image. I'm going to right-click and go plot, and I can define a NumPy function for manipulating the two-dimensional data that's been plotted. And if I use this with the slicing tools, each slice is sent to NumPy, and then sent to Python to NumPy, and then it can be manipulated. So what I'll do is I've got an existing one, and okay. So the image has changed. So what's happened to the image? So let's have a look at the Python I just filtered it with. And this actually debugs as well. I need to start the debug server for that, but you can debug. Basically what I've done is I've clipped it between 1 and 80, which is why that's changed. The other thing we do have as well is just you can type expressions directly in, like I showed you earlier, but there's also like some image processing algorithms, so we could potentially do the Sobel filter. And that's going to take a while. Which of those of you who don't know about the Sobel filter, then I don't either, so no point asking me. No, I believe it's an edge detection algorithm, so it highlights the deltas between features in the image. Okay, so you see there, you can't see very much. That's not surprising. Yeah, so we can see there it's detected some features which, using the algorithm, has brought out the spots. Okay, so in summary, we have a feature called workflows, but there won't be time for questions if what the hell. So we have some workflows based on something called Ptolemy 2, and I'll quickly show you that. So this is basically pipelining together some of our maths. So if I quickly run that, these are images that you can just click and drag into the file, and it basically sends their data off into a pipeline. And you can also slice, so you can have, if it's a stack of images, you send them off one by one, and you can define the slicing for that. So if I run that, now how this works is uses the Java debug thing. So what's happened here is done the maths on those images, multiplied them together, added them and so forth, and put them into an HTF5 file so we can have a look at them. Yeah, and because I've got I probably need to change this over to mean. There we go, so we can see that. Okay, so in summary, thanks to Eclipse providing a great tool. We think that this RCP stuff is really fast and scalable, and we like using OSGI. We think that's a great way for doing what we're doing, because we can have lots and lots of GUI sat on disk and only load it as the user needs it. And we tend to have all sorts of different tools and things which are there, so it's a great technology for us. And we thank the Java community as well for its APIs, and we're looking forward to Java 8. That looks great. So thanks a lot for listening, and any questions?
Yes. Yeah, maybe if we look at the first picture, so the British Secret Service has also round building. Is there some misunderstanding in the last feature, or are you not infected from it?
So I know who you've been emailing, so that doesn't. Yeah, no, I mean, no, it's not related.
Is everything done on your local computer, or do you need servers for computational methods for rendering pictures?
Yeah, no, everything I've shown you today is just half gigabyte download from our website, so it's just a straight Eclipse application. Now we do have things which use services, use our supercomputer, our clusters and our whatever on site, but I haven't shown you those today because they won't work unless I'm on site. But, some of them will. You can SSH in and things, but in general. But yeah, so all the visualization is just happening on this machine, and what we're trying to do is, if you're interacting with very big files like these gigabyte files, obviously, fundamentally, you only actually need to have in memory what the user needs to color each pixel. So if you're making a GUI app, you don't actually need a hell of a lot of the data in memory. So it's just about all the time trying to code it in a really abstract way. It's the code becomes very different when you haven't got the memory to visualize what you're trying to look at. Yes, sorry, it's two at once. Do you want to go first?
So everything we've seen in the dawn side, what you can have on GitHub? Or?
Yes, everything we've seen today is on GitHub. We do. How big? It's about 750,000 lines of code at the moment, but it's growing quite fast because last year it was 500. So.
Which license?
Some of it's EPL and some of it's Apache, but they're both permissive, so you can use them commercially. We welcome commercial partners. I mean, we are funded by taxpayer money, and we'd very much like to, have some commercial partners. That'd be great.
That's
yes.
Great. I think we had GPL before.
Yeah.
Now switch to EPL and Apache.
Yeah. That's right. Well, we'd like to be only EPL. There's 2 more questions at the back.
About Jeff, you're using Jeff for drawing diagrams.
Yes.
For drawing diagrams, and I saw soon you're going to use Graphiti.
We are. Yeah, for the workflow. For the workflow stuff I showed you with the the rectangles and the lines between. I showed that briefly at the end.
For the main processing, you use the
XY graph. It's, if you know Eclipse Nebula, there's a new
it's a library that aims to provide both RCP and RAP components.
Yeah.
And did you choose XY graph because you plan to move on the web?
Yeah, we would like a wrap version. We have a prototype for that.
So it's in your future plan?
Yeah, we have a prototype for it. We're not sure exactly how we're going to do single sourcing, and we're also not sure about a few other things about where the developers are going to come from. But that is something we'd like to do. We haven't. Yeah. Yes.
Are there any plans to include some sort of volume rendering application?
Yes. So we're planning next year to start using JavaFX. You've seen the surface stuff, but what we want to do is ISO surfaces. That's the next thing, and we don't want to do that in Joggle. We're fed up with Joggle. It's not the way forward. But JavaFX seems to now have a better scene graph than it did in the last version. So we're hoping to do volume rendering with that. But there's a bit of hand waving there because we haven't started on that. Yep.
Are other facilities like this using? Do you know what are other people using if they're not? I guess my question is, what are other facilities? What's their technological approach? You know?
I think Python's quite popular in general. So they've got a lot of, and I know ESRF are doing Python visualization as well. All the GUI is in Python, Python Qt, Python visualization. There's not that many in Eclipse RCP. There's some activity in America, but also a lot of Python over there as well. So.
Because this is a completely new. This was a new exposure for me, just hearing all of this. But it seems like you could qualify that type of the application as sort of a specialized image processing, full-featured, specialized, industry-specific image processing application. Yeah. Would that be a fair way to qualify?
Yeah, I mean, one thing is, I said at the start that there's other applications which we make on site, but they need visualization as well. So we have the data analysis algorithms needing visualization, but we also have the data collection. And when that runs, it produces one-dimensional data most of the time, and that they need to see a real-time plot of that kind of stuff.
So for perhaps like medicalMRI.com, it would have the same type of application?
Yeah, it's not used in that scenario yet, but there's no reason why not. We have file loaders contributed by a service, and you can you have an extension point to say, I want to load a file of this type, and you have an interface to implement, and then the rest of the code pulls the file loader service and says, give me the data from that file. So that's how we extend stuff. So our collaboration is across several facilities, and some of them, 2 of them, have their own file types, so they write their own loaders for those, and then the data's just erased at the end of the day, so, it's just a case of pulling it in.
One last question, are you using, or you plan to use Eclipse E4? Maybe you're ready for that?
Yeah, we would like to migrate to Eclipse E4. I know Philip's already done it with OpenCrom, so we'd like to follow, but it will take us a while. We've got a lot of developers that know how to use Eclipse 3. We're using Eclipse 3.8 as our platform. I can't see it happening next year, but maybe 2015.
It's not that it's very nice to be used.
Yeah. Yeah. Yeah, we use it for IDEs, but that's not our platform at the moment. Okay. Thanks.